Control is an issue that at times is important. So we will look at some of the control issues. And I have here contact with Melina, and we are looking at the tab where we have all the control parameters. And the most important one is velocity control, how to control the wheel velocity. And if we open that, but just by clicking, we can see that this is a PID controller. We have on our wiki this overview of the control settings that are available. This may look a little bit complicated, but over here we have the input, we have a pre-filter, and if we skip that, then here we have the comparison between what we want, the reference, and the measurements. And the measurements come in here. So this is, if this is velocity control, then this is the velocity we want. We can filter that, but if we don't, then this is what we get here at the reference. And the measurement is the actual velocity measured by the system. And if there's a difference, we have an error, and we multiply that with a proportional gain. So we have a filter here with a numerator, a zero and a pole. And what we can control is the time constant in the zero and the time constant in the pole. But it means that at low frequencies, where S approaches zero, we have a gain of 1. And these, at higher frequencies, we can then increase the gain or decrease the gain. We can increase the gain if it's a lead, and if we decrease the gain, then it's a lag. We can also insert an integrator, the I part, and what we can control there is a time constant if it's there. And then we have the opportunity to have a pose integrator. Usually we don't. And there is an additional gain here, and that's usually just 1. So this is totally ignored. And then there's an output limit. And if it's a velocity control of the motor, then this limits the voltage that the motor can receive. And the U here is the motor voltage. In the feedback path from the measurements, we can add a filter. And we have that in the velocity control. And again, what we can set is the time constant in a zero or time constant in a pole. If we set this time constant in the 0 to 0, then we just have a pole, and a pole as a low-pass filter. And we can use that to filter away some high-frequency noise that may be in the measurement. And for the velocity, we do have that. We also have a feed-forward. That means if we want a certain velocity, then we can multiply that with a constant, kf, and we can send that add it directly to the output voltage, assuming this filter is 0. We can also add some filtering in the feed-forward, but usually we don't do that. So let's get back to the filter that we have, the velocity filter that we have here. And we can see we don't have any post integrator, we don't have any integrator, we don't have a lead or lag in the forward path. And now we have, in this case, also removed the output limit. Let's put the output limit back so that it was, like it was before. So the only filter we have is in the feedback path, where we don't have a 0, but we have a pole with a time constant of 5 milliseconds. That means a low-pass filter corresponding to 5 milliseconds. We do have a KP in a proportional gain of 15, and we do have a constant feed-forward gain of 4, and these settings are usually quite good. So we leave it there. And then we will have a look at how to control when following a line, follow edge. And that's more important and also a bit more difficult because the control parameters are somewhat speed dependent. So in here we also have we don't have any feed forward, but we do have a P gain of 0.3. We have a lag filter implemented here in the forward path. If we keep the mouse on top of that, we can see the DC gain is 1 in any case, lead or lag configuration. And in this case, when we have high frequencies, we can say that this is a numerator and this is a denominator. And that means that at high frequencies, we have a gain of 1 divided by 5, which means that we can have a higher KP without having any stability problems than we would have without this filter. And that means that we can have a higher or a less error, stationary error, by increasing the KP, the proportional gain. We do have also in the feedback path, we have a lead, which means that when it that would dampen. This is to dampen the overshoot. Whether you can try to change these two filters or you can remove them, we will keep these two filters as they are, and we will only experiment with the KP to see what is the effect there. So that's it. We will stick with this filter. There is a default filter in your robot. It may be a little bit different than this, but this is a possibility that we will try. So, and to see how it works, we will make a mission. So I'll go to the mission tab, and I have here a mission we use for testing. And I'll go through that. We have to start with a velocity of 0.3 meters per second, and we'll run for 0.1 meter. That means we'll just keep started at a fairly low velocity. We'll keep that velocity for a further distance of half a meter or until the line is valid. Line valid equals 20. So a good stable validity of the line for 20 samples. And then once we have detected a line, we will continue to follow the HL, the left side of the line. And it's a white line. We cannot do anything but white lines. And we will continue to do that until the line valid is below 4. That means we have lost the line. So if we lose the line at any point, we'll continue, and we'll continue with the next line here in the script, in the mission. That means stop. Okay, so this is the mission. We will save it to the robot. We can also save it to Flash to make sure that it's there after a reboot. And we'll see how it works. So I have placed the robot at the start of a line, and we should follow the left edge. And if we have calibrated the crossing line correctly, it'll just continue crossing after this crossing here. And the left side, that means we should go this way with a lot of swings, a lot of turns, and also sharp turns. And we should end down here, and when it loses the line, it should stop. So let's see if that's what happens. I have the remote control here, and if I press the green button, it should start. And it seems to follow as I predicted it would. I have, of course, tested it, so it's a little bit cheating. We are going slowly forward, and it stops at the end. So then we will try. Could we do it faster? And now it comes good into play that I will change the velocity to 4, and maybe we'll just put the velocity, start fairly slowly, and then increase the velocity. We'll try this, and I will go back and start again. Whoops, we'll turn around, something like that, and see if it works. And it maybe it's not really visible that it was faster, but it was. And now we lost the line. The LED turns off once we have finished the line, so we must have finished the mission here. That means that with these control settings, we cannot go 0.4 meters per second, at least when it's so curved like this. We can try following the other side of the line, which is much more smooth. Then we should go this way and stop down here somewhere. We can add the other camera where we can see the end of this line here, and it should then stop just in front of this small camera. So we'll try that. We will modify the mission so that we follow the right lane, the right side of the line. So I'll change the HL to HR and save that to the robot. We will try that. I will take control and go back to the starting point. Something like that, and press the start button. So now we follow the other side of the line, and that works fine. We stopped just when the line finished, or the line sensor couldn't see the line anymore. So we could do that, but we could also change the control to see if we could be more accurate. So I'll change this KP to 1. That means increase it by a factor 3. And we'll see if that helps. And we'll turn it back so we follow the other side of the left side again. So I'll change the mission. I'll change the mission so that we follow the left side, save to robot, and then press start again. And it could be too much, but it seems like it's working just fine. You can see that it may be zigzagging a little bit, so maybe we are close to the stability limit, but we can try with a higher speed. We can increase this one to 4, to 6, and to 8. Oops, you cannot see what I'm doing. I have now increased the start velocities to 0.4 meters per second. Then until we detect the line, 0.6, and then go to 0.8 meters per second and save that to the robot. And we will try again. Oops. A little bit further back. Something like this. And we'll... So now it goes somewhat faster, but it can still follow this already curved line. We can see, we can try what is the limit, and I will change this to 1 meters per second. Oh, maybe we could say 1.2. Then no, let's start with 1 meters per second. I've saved that to the robot, and I'll move it back to the starting point. Yep, and we will try it again. So Now something happened, and we can see we are not finished with the mission because the blue light is still on. So what happened? What's the problem here? And I can tell you what the problem is, and we can fix it. If we go back to control, to the velocity control, there is an output limit of 9 volts, and that's a maximum voltage that we are allowed to give to the motors. But there's another feature that are not included, not visible here. It is if we have exceed this 9 volts or are at 9 volts for more than, I think it's 1 or 2 seconds, then a safety system will say that we are not doing good, and it will disable the motors. And when we are disabling the motors, the mission will stop. We say we would like to continue until the line is no longer valid. The line is valid, but the motor is not running. So that's the problem. We will simply remove this output limit because this is meant to protect the motors, but these motors are 12 volt motors, so they can take whatever we put at them. So we'll do that. We will save to flash, and then we will try again. I will take control and move outside where there's no line, and start the mission, and then there's no line, then the mission stopped, ended. So we will try again and press the green button and see if that's better. So now we continue, and it could actually follow at this speed, this curved line. And it may be possible to do it even faster. But basically, this is it. And it also means that when we were above 9 volts, that we are close to the limit of what this robot can do. If we want to run much faster, then we need bigger wheels. But that's quite another issue.